Oh. Um, can online people hear me? Hello? Hi, online people. Can you guys hear me? Okay, amazing, amazing. Okay, okay, cool. Testing, testing. 1, 2, oh, okay. Can you guys hear me clearly? Okay, thank you. Oh my gosh, it's my first time setting all this up and it's just really hard to work with. Apparently this camera is meant to be AI and tracking faces, but it's not tracking my face very well. Let me try and fix that again. Just one more time. Give me 1 second. Sorry, everyone. What if I just went? Is it working? It's working. Okay, yeah. For now. All right. I'm just gonna move it over a little bit. Wrong one. All right, I think we can start. Online is all good, right? I think. If not, just shout at me. Sound only from left ear. Only left speaker? That's concerning. Is that for everyone on the stream? Let me look. Oh, okay. Someone's works in both ears, so I'm just going to assume that it's a one few people problem, as long as you can hear me, because I think I've set it up right. Maybe I haven't, but let me know if you can't hear me. What? Okay. There's too many people saying there's only left ear. There's no settings to change it, so I think. Okay, I'm gonna leave it as the left ear now. Maybe your right ear is gonna be a little lonely, but hopefully for the Friday lecture, I'll make it your right ear instead of your left ear for everyone online, because we're getting into the lecture time. So hopefully you can still hear me with one ear for now. I'll sort that out in the future to make sure that it's both ears. All right. Okay, where to start? Okay, let me just mute my phone, just make sure everything's ready. Okay, there we go. Hello, everyone. Welcome to this week's lecture. So today's lecture and Friday's lecture will both be taken by me, and then Sasha will be coming in to take next Monday's lecture. If you were in the lecture 2 weeks ago, Jake would have told you guys at the end of the lecture that he is taking a break because he's taught so many terms, like consecutive terms for like so many terms already. So he's getting a break, and Sasha and I are taking some of the lectures. So if I go too quickly or too slowly or anything, just let me know. This is like my third term doing this. I've only taken like 2 lectures so far. So just bear with me if I stuff anything up, including the camera. I don't even think the camera's pointing at me anymore. It's just pointing downwards, and I've kind of given up. Okay, so just a little bit of an intro about me. I am Tammy. You might find that I seem familiar if you're in my lab. Yes, I am the same person as the person you see in my lab if you're in there. I'm one of the course admin out of the 3 course admins for this course, and I currently am doing a PhD in something called machine ethics. Okay, computation and machine ethics. If you're curious, you can have a look or you can talk to me after. But yeah, so today's lecture is going to be about mainly dynamic memory allocation. So we're talking a bit about memory, and this is going to lead on to the idea of linked lists, which is very exciting because linked lists is like my favorite topic. But yeah, before that, we'll do a pointers recap as well, because we know like there's been like a flex week in the middle and everyone's stressing about their assignment. Is anyone working on their assignment as I'm speaking right now? That's very relatable. Well, for those who's already finished or is like, I'm done, I'm not doing anymore, that's awesome. If you haven't started or if you forgot that the assignment is happening, please remember the assignment deadline is tomorrow at 8 p.m. So if you haven't started, get on with it. Okay, let me just, yeah. Again, if you have questions about your assignment, you don't, like, not only can you go to the labs, you can go to the help sessions. We have some today running, and we have some tomorrow running as well. But they're going to be super busy because everyone's like coming in for last minute questions for the assignment. Yeah, just a few announcements. The next thing is, unfortunately, you're not going to get too many days break between assignment 1 and assignment 2. So assignment 2 will be released at some point near the end of this week, okay? Some point. And then next Tuesday is going to be the assignment 2 live stream. So that's where we'll introduce you to the assignment. So it's going to be a linked list. So we haven't covered that yet. If we get time today, I'll briefly introduce it. Otherwise, I'll introduce it on Friday. Very exciting, I think. The live stream is going to be hybrid. We will announce the location of the in-person one if you're keen to come in person on the forum, on the Ed forum when we get a bit closer. And then the next thing is, I think the revision sessions, I don't know if everyone's heard about revision sessions. Some of us may have, some of us maybe haven't seen the forum posts. But there's revision sessions happening. They happened last week, and they were very popular, all booked out. There's more coming, so we're organizing more. If you don't know about them, please check the forum because we post a lot of announcements and sessions, extra help session information, extra revision session information on there, just like, you know, to help everyone out. So if you're lost and stuff, revision sessions are the best place to go because they're there to cater for like helping you catch up and stuff. Okay, so I think you've probably seen this QR code before, so I won't explain too much, but this is a research project that's happening. And again, if you're interested, you can scan the QR code or you can scan it in on your own computer because I've uploaded the lecture slides as well. And again, live code, you can, when I'm coding, you can access the code, I think, hopefully, if we set that up properly. You should be able to access the code that I'm writing as I am writing. All right, so let's begin with today's content then. So 2 weeks ago, you started pointers. Now, we're going to recap pointers today, and then we're going to do some memory stuff to lead into linked lists. Before I go on to the next slide, I just want to get a hands up just to gauge everyone here in person, who is like, I am super confident about pointers now, I am a pro? Anyone feel like that? Maybe? One or two? Who's like, I think I'm getting there, like I'm understanding the concepts, I just need a bit of time? Okay, there's more people that, who's like, I have absolutely no idea what's happening with pointers. Like, I don't know, it's very confusing kind of thing. No one's putting their hand up? Oh, I see a few hands now. Yeah, so, in my opinion, pointers is one of the harder topics in this course, and it took me like weeks to understand it. So I did this course back in like, I did this course in 2017, so that's a while back. But pointers was like one of the hardest topics for me, so if you don't understand it now, don't panic. Please do ask questions as I'm explaining now, or you can ask questions afterwards, because the point is to help you like listen again and again and again. You might understand 10% first, and then the second time you understand 20% of it. Eventually you get it, so yeah. So just talk a little bit about pointers. So pointers are a type of variable that stores memory addresses of other variables. So then you can lead, so if you access that particular pointer variable, it's going to direct you to a different variable. And that becomes very useful, especially when we're doing linked lists. And you can figure out why, and you will understand why it's useful today as well. And it can point to, so when we're saying point to, it's storing the address of some variable. It can point to any different types of variables. So for example, your integer variable, it can point to or direct you to a char variable, it can point you to a struct, and so on. So that's your pointers. Now, I like to think of pointers like a little bit like toilet signs or signs, where they direct you somewhere else. It's like they direct you to address, in this case, it's literally, you can think of it as like the address of your home, address of, instead of your home, it's the address of a particular data in the computer. They live somewhere in the computer, kind of thing, in the memory. But yeah, so then with that, with pointers, because you have that direction, it directs you to a particular variable, you can now access the data of the variable via that pointer, via the thing that directs you, right? And you can get the address of where that variable is, and so on. So there's actually three main syntax, I would say, with pointers. And just a little bit of a recap, you might look at this and be like, I already know this, or this is familiar, or you might be like, I forgot everything from last week 5. But the first syntax is this asterisk thing, okay, asterisk. So when you see the asterisk, I always remember never to read the asterisk alone, okay? So that asterisk doesn't belong to the num underscore pointer bit. This is declaring a pointer variable. This bit, the int space asterisk, is one thing. That's like the type of the variable. So this is saying that, hey, this is an int pointer variable. This is an int pointer type kind of thing. So that's the first notation we have for pointers. The second notation we have for pointers is this ampersand thing, okay? That weird syntax thing. Weird ampersand syntax thing. Where this is what we might do, one of the ways we can initialize pointers. And so this example here is, let's say we've declared and initialized a integer variable. Then we can have a pointer, assuming that we've declared it before, that points to, or that stores the address of the number variable, of the int number variable. So this is saying, hey, the number pointer variable is pointing at the number variable, kind of thing. Maybe I shouldn't name them too similarly, but yeah. So if you look at the second line, that image on the right kind of reflects that. So you've got the number pointer variable inside somewhere in the memory, and I've kind of hand-drawn my arrows, so they're kind of ugly, but it leads you to the number variable, which has the value of 8, kind of thing. And then the third syntax we have is this asterisk again, okay? So this one, this asterisk, is different from the asterisk above. Where this asterisk, when you see it alone, without a type in front, so that one had an int in front, when you have it without the type in front, it means, hey, can you go to the variable that you're pointing at and get the value of that variable, okay? Get the value of that variable. So You can see arrows pointing at like quotation marks things. That's how I usually remember my pointers syntax. So ampersand means, hey, the address of number variable. Whereas the, what you call this, asterisk means the value in the variable that the pointer is pointing to. So the number pointer is pointing to some variable, and what is the value in that variable, kind of thing. Not sure if that makes sense, but hopefully it did. Let me know if you have any questions. You can stop me at any time. But yeah, emphasize again and again, those two are different because that confused me for so long. This asterisk and this asterisk, they mean different things, okay? And keep in mind that that's a variable type, so we read that together, like I just said before. So does anyone have any questions about pointers or want me to explain anything in particular about pointers? Yes?
When you pass a pointer in a function,
Yes.
am I declaring it or am I dereferencing it?
That's,
The argument.
so what's happening when you are passing, so the question is, repeating for the online, when you are passing a pointer into a function, what is actually happening? So what's actually happening is so just like any other variables, you're copying the content of that variable over. So what you're actually doing is you're copying the address stored in that pointer variable into the pointer variable inside that function. Does that make sense? So let's say, I'll just do a quick thing. You know what, I'm just going to use my hello.c from before. Let's say if I had some function called, I don't know, sum, and I passed in some pointer value, like let's say I passed in, int number equal to 8, so that's my integer. And then I have an int pointer, number pointer, that's pointing at the address of this number, right? That's what we had on the slide, similarly. And so let's say if I were to pass into, assuming that I've, have my function prototype and stuff, I'm not gonna write it out here, but assuming I have a function called sum or something, or I don't know, I'm just calling it sum because that's the first thing I thought of. And we pass in this number pointer thing, like that, right? Let's say like that. Then in my sum, what we actually get, okay, is I can call this pointer as well. In my sum, what I actually get is this, when I pass this in, the number pointer's address, which is the address of number, is going to be copied into this pointer here. This pointer, which is the variable, the pointer variable within this function, this sum function. Does that answer your question? Yeah. It's very roughly coded out, so the other stuff won't make sense, but I'm just trying to show the main bit. Yes?
When I was trying to use pointers in the assignment, it asked me to initialize the pointer. So how do you, it kept saying uninitialized error.
So that's, did it say like accessing uninitialized value, pointer value?
It was asking me to initialize the pointer, but how do you initialize a memory address?
Yeah, so this is an example of a way to do that. So if you have another variable that you already have a value in and you want that pointer to point the address, line 6 is one way of initializing. Another way, which we'll learn about today, soon. I'll answer your question soon. And if it's specific to your code, like after today, if the question doesn't get answered, feel free to like just come over after or like go to a help session and show me the code and I can help you. No worries. Any other questions? Otherwise, I'm gonna quiz you guys. All right. Let me move on to the next slide. So, before I move on to something else, because we're going to use pointers today, I just wanted to really make sure that we understand or we're getting there. Mini quiz. So, will the following work in code, okay? So, I've got a declaration of a number, and I've got a declaration of a number pointer, like I did before. They're not initialized, but let's just, like, it shouldn't matter in this context, whether they're initialized or not. Maybe. But let's have a look. So I'm going to get everyone to, so in the chat, I can see the chat as well. So if you type yes and no and stuff, I will see. So for everyone in person, I'm going to say, each one of them, and you're going to have to put your hand up for yes or no. So first one is number pointer is equal to number, like that, just like that, number 1. Who thinks that, yes, this is going to work? Who thinks that, no, this is not going to work? Who's not sure? Okay, let's have a look. So, no, they're not going to work. And the reason why they're not going to work is if you have a look at number pointer, we always look at the types. You can only assign something to another thing if they're the same type, right? So if you look at number pointer, that's an int pointer type, whereas number is an integer type. So no, they're different. What about the second one? Yes for you think it will work? Answer? No for if you don't think it will work. Okay, there's more hands. What about online? And if you don't know. Okay, so the second one is, yeah, that a lot of us are correct. No, it's not going to work. Again, they are actually different types. It's not that obvious, but the left-hand side, remember the asterisk is meaning, hey, go to the thing that the pointer is pointing to and get the value of it. And the thing is pointing to an integer number, so then this thing is actually an integer on the left-hand side, as opposed to the right-hand side, which has an ampersand in front of it and saying getting the address. So that one's, they're both different types on both sides. The third one, yes for work. It will work. Okay, thank you. No for it won't work. All right, we have no hands for this one. I mean, that's good, because the answer is yes, it will work. This is the way I showed you guys before, so that means you guys are all listening. Hello? Yeah, what about the last one, final one? Yes, it will work. No, it won't work. Who's just guessing and just 50-50? All right, so no, it doesn't actually work because what's actually happening is when you do an asterisk in front of number pointer, this thing now becomes an integer type because number pointer is pointing at number. If we make a point at number with line 4, actually, sorry. Yeah, sorry. Yeah, so if we dereference, let me repeat that. That wasn't clear. So if we have an asterisk in front of number pointer, we're saying, hey, go to the thing number pointer is pointing to, and then and get the value of it. So then that doesn't make sense to equate it to some value already, because the left-hand side is trying to get the value of something. So basically, that's invalid syntax. The only one correct here is line 8, sorry, the third option. Yeah, so that's the quiz. I think generally we're slowly getting pointers, but if you don't understand it or if you're still a bit stuck, it's okay. There's a lot of practice this week on it as well in the labs and shoots. Okay, so today's big bulk of content is about dynamic memory allocation, and it will answer that question about how do we initialize pointers. So before we move on to that, there's a lot of prepping towards that. So we need to examine how our memory, what the memory is kind of looking like when we're running a program. Okay, what's actually happening in the memory when we are running our program? And note that we don't actually do any of this when we code. It just does it itself. Okay, when we, run the code, execute the program. So you will learn more about this in 1521, by the way, if you're interested in this low-level things. But this is what the memory looks like, okay, or what it's designed to look like, where we have something called a stack, okay? So memory is divided up into 4 components. We have something called a stack. We have something called a heap. We have something called data, and we have something called code, okay? Now, you can see the arrows kind of going up and down. What that's trying to say is these two, the stack and the heap, can shrink and grow. So the amount of space they take up in memory can be different at any point of time. Whereas the data and code sections in memory are already fixed size, okay? And specifically, the arrow directions actually are important as well, because the stack is actually growing down, okay? You can kind of see that I've kind of labeled the high address and low address. What that means is like the address meaning where, where a particular location in memory is like the address of the memory location. So low address means like, for example, 0 is like the lowest address kind of thing, and high address is something, a bigger number. I can't think of a hexadecimal number on the top of my head, but there's one later. You will see later. But yeah, so the stack is growing down in the memory, and heap is growing upwards, okay, kind of thing. This is kind of the diagram. And the general vibes of what each one of these does is the stack is for anything to do with our functions. So if you have declared variables in your functions, if you have parameters in your functions, all that data is stored inside the stack, okay? What the variable values are and so on is stored inside the stack. Then the heap, what the heap is Malloc object, which we'll cover today. Malloc is a very important concept. It stands for memory allocation. And so anything that's Malloc, buzzword right now, is going to be stored inside the heap. And then we've got data. It's a very vague term here, but it's basically storing your global variables, which we don't use in 1511, static variables, we also don't use in 1511, and constants, which we do, the hash defined constants itself, okay? And then you've got code, so your machine code for your program, so the actual instructions for running the programs. So that's what the memory looks like in general. There we go, okay. Yeah, and as I said, it grows and shrinks, the stack and the heap, and whereas the data and code is fixed size in memory. Okay, so let's talk about the stack in a bit more depth. So the stack, like I said, is where the information about your program goes. Anything about like what functions are called, what order are they called, so which function gets called first, what variables do you have in the functions, what values are those variables in the functions, and so on, which function are the variables in, everything like that is stored in the stack, okay? When a block of code is executed, so generally we're talking about like functions. When a function is being executed, called, we have something called a stack frame that gets created. Not the most accurate way to describe this, but I always think about it as like stack, stack of plates in the kitchen, like you're stacking plates. So if you're calling your function, you're adding your plate on top of the stack, kind of thing. So every time there's a function call, a stack frame is created and added onto the stack, okay? And that particular stack frame will store all the relevant information to that particular function call. There will be a specific example to explain that in a second. Now, when that function returns, so when that function ends, that stack frame is now removed from the stack. So it's kind of like taking a plate off the stack of plates, kind of thing. And anything inside that stack, so if you have variables, variables, values, different stuff, everything gets destroyed, okay? When you return all those variables that you've declared in your functions, as you've probably experienced so far, like doesn't exist anymore, right? After your function call. So that's your stack. And so what I want to do is take us through a code run-through of what's actually happening in the stack, okay? Keep in mind the stack is only one out of the 4 sections we have in our computer memory. So first thing, let's just have a look at what this code is doing, because I just shoved a bunch of code in everyone's eyes. So what this code is doing, it's a bit random in a way, but it's been designed to kind of show you how different things behave when we're in the stack, kind of thing. So there's pointers in here, there's variables in here, there's a function call in here, and basically, if you have a look, so we're initializing 2 variables, we're kind of making a pointer that points to one of those variables, and then we have a function call that takes in the num1 and num2, so the values of 1 and 4, and gives us the sum, right? Returns us the sum. That's what's happening there. So if we want to execute this program, the first thing that will happen is the operating system will call our main function. That's how we start executing the program. So main function is a function. So it is going to create a stack frame and put it on the stack, okay? So this purpley blue, I don't know if it's purple or blue to be honest, but this thing is being added onto the stack. Next line, we have a int num variable being created. So that's allocated some space within the stack frame for the main function, as we can see on the right-hand side. And then similarly, with line 8, we've got another variable that's been declared, and this time initialized to 1. So that value gets stored inside the stack frame of the main function, on the stack kind of thing, and all that information is getting stored. Similarly, num2 as well. So you can see on the right-hand side it's changing. And then here, okay, so we just transition like this. Here, what's happening is we've declared a num pointer variable. And because it's a pointer, it stores the address, or it directs us to another variable, right? It leads us to another variable. So I've indicated with an arrow that it's going to lead us to num1 if we try and access the pointer address and go there. So that's also stored on the stack. And now the interesting bit is here, okay? The next line is actually a function call. So what's actually going to happen is, I have a question actually. Do we go on line 12, do we read from left to right, or does it read from right to left? So does it read the right-hand side first or the left-hand side first when we're executing code? Left to right? Well, we read it from left to right, right? But when the program is doing calculations, does it need to know the right-hand side's information first or the left-hand side information first? Right-hand side, okay. I have chocolates here, but I'm really bad at throwing chocolates. So I'm just going to throw it to you. That was so terrible. Thank you so much. Yeah, as you can see, I'm really bad at throwing chocolates, and I've just dropped the chair. But there we go. Okay, we're good. I'm so chaotic. Oh my gosh. All right, moving on. So yes, exactly, the right-hand side. Okay, so we need to know the value before we assign it to the left-hand side. So what's going to happen is we call the function, and like I said before, when we call a function, we're going to create a stack frame and put it on the stack. So you can see from the previous slide until now, on my right-hand side, the diagram has changed, right? I've added a new stack frame. So that big bubble is my new stack frame. And inside it, I've added two, it's storing the variable a and b and the values of 1 and 4 respectively for them. Because when we're calling the function num1 and num2's values, which is 1 and 4, gets passed into this function, right? So then a becomes the value of 1 and b becomes the value of 4. Like, just how functions work, right, in general. So those values are getting assigned. And then moving on, we kind of add them together, so a plus b, which is 1 plus 4. Then we get 5, and that's our sum. That gets stored in our stack frame. And then when we return, okay, see the difference? So this is before we return, and the reason why I've circled this gray is because we're still inside that function call, right? We're still in the function at this point. We're on line 2 right now. And then, yeah, when I return, as soon as I return, that stack frame gets destroyed. I don't need that anymore. All the information in there, like sum, that int sum is gone, right? Because that int sum was here, inside the stack frame. So as soon as I return, that sum is gone, and the value of that sum gets stored inside our total variable, which is inside the main function, right? A different stack frame. Does that make sense? Does anyone have any questions so far? Okay, cool. All right, so yeah, that assigns the total. And so my question is, there's one more step here. What is the last step here? We've got on line 14 return 0. So what's going to happen to our stack on line 14? It's going to get destroyed? Exactly. But now I have trauma. Wait, one sec. Let me just move on to the next slide. There we go. It's going to get destroyed, exactly, because we don't need all that stuff in the function anymore. The program has ended, and oh yes, okay. Claps for myself. Thank you. I never imagined I'll get clapped for throwing a chocolate bar, but okay, thank you. Yeah, so exactly, the stack frame is, destroyed, and the memory is returned back to the computer to use for other stuff or other programs and so on. Okay, so that's what we've learnt so far and how it happens in memory kind of thing. But with what I just demonstrated, we kind of need to, so stack frames are generally fixed size, okay? Before you execute the function and stuff, you already know, like the computer will already know how big the stack frame is. But there are times where we want to be able to like allocate memory of whatever size we want, for example. If you recall assignment 1, I don't know if how many of us had this issue, or even just in general labs, where you will declare an array. And you're like, what size should my array be? I don't know how many numbers I'm going to get, so I'm just going to declare like a really big sized array and just hope for the best. Has anyone done that before, or is it just me? Okay, I can see who else, right? That's like very annoying, right? And then you never know. Yeah, so we need some way to resolve that, okay? What if we can ask the user, hey, like how many do you actually need? And then get the appropriate amount of memory at runtime, right? Additionally, this way that I'm about to introduce allows for a more permanent way to store your values, okay? More permanent meaning before, when the function call ended, the variables in the functions got destroyed, right? Like, they disappeared. But now, this way I'm about to introduce, they stay even if your function returns, okay? You can keep them under control for as long as the program executes for. Or you can ditch them. It's up to you whether you want to keep them or ditch them, kind of thing, which is quite nice. I'll get there about how we do that, because we need to first talk about the heap, which is where that happens, okay? So that's the next section in our computer memory, the heap. And it's memory. It's a part of memory. It's a large block of memory that sits outside of the stack. I'm reading off the slides. So in here, like I said before, nothing is automatically declared or destroyed. So I said that you can like request for more memory anytime you want, and you can kind of like give back the memory under your control. Like it doesn't, like when the function returns, it doesn't mean that the memory is given back and so on, destroyed and so on. But the consequence is that nothing is automatic. So everything is done manual when you're controlling your, the memory space like that way for your program. So, there's pros and cons. It's kind of annoying sometimes. And how we do that, okay, how we actually have that power in our hands is using this function called Malloc. Buzzword. Malloc stands for memory allocation. And what it does, okay, it's a function that takes in one argument that specifies how many bytes of storage space you want. Yes?
Does it fall under the standard I/O?
Very good question. I was going to test you guys after, but that's a really good question, so I'm going to throw a chocolate. It does not. It does not. It falls under the standard library, stdlib. Yeah. stdlib.h. I'm getting better. Okay, cool. So, now I forgot what I was talking about. Yeah, anyways. So, yeah, Malloc, it takes in how many number of bytes you want, and then the computer's like, okay, you want this many bytes? Let me look for some space. And it will give you a particular, return you a memory address that has that amount of space that you need, kind of thing. And if it doesn't, then it will tell you that as well. Which is very nice, because it allows us to ask for memory whenever we want in our program. And I've got like a very basic example of lines of code of what it looks like. And look at that, I forgot my semicolon. I don't like that. But anyways, so yeah, Malloc, number of bytes we want, for example, 1,000 or something. But that's not the way we would usually do it in 1511, okay? So I'll show you how we actually do it. Because if we just malloc 1,000 bytes, what are we going to do with 1,000 bytes? We want to ask for memory for like a particular purpose, right? So we'll see that in a second. But like I said before, because the power is in your hand now with controlling memory, I can see some face palms, I'm sorry. But the power is now in your hand, so you have a greater responsibility when you're working with memory, okay? Which is, if you're asking the computer for memory, you need to keep track of whether you're using it or not. As in, once you don't need it anymore, or you can't just, just say, okay, I'm just going to put it aside, leave it there. You need to free it. You need to return it back to the computer, okay? Yeah, so you need to call this function called free, which basically just gives the memory back to the computer. So then we can prevent something called memory leaks, okay? Because if you recall what I said before about Malloc, it returns the memory address of the block that it's allocated to you. So let's say if you had a pointer that was pointing to that memory address, right? And then later on you're like, wait, I want this pointer to point somewhere else. I don't need this piece of memory anymore. And you just change that pointer to point somewhere else. Then this piece of memory is just going to be floating around now. There's like nothing pointing at it. And it's just going to be a piece of memory that you've hogged in your program that's doing nothing and you can't reference it anymore. And it's like junk floating in space kind of thing. It's taking up space. So we need to make sure we prevent those kind of situations, which is what we call memory leaks. And we have a way to test that when we're compiling with DCC. I'll demonstrate it later. But yeah, we want to prevent memory leaks, so we want to use free. Main takeaway is whenever you're using Malloc to allocate memory, you should always have free in your program. And I think from my experience, how I check is like how many times I've called Malloc or how many times I've written Malloc. This should generally be the same amount of times that there are frees, because you're freeing different things, mallocing different things, and so on. But yeah, and you can see on the bottom right, it's very simple to free. You just free and then put the pointer that's pointing at that particular piece of memory that you want to give back to the computer there. Okay? Okay, small aside, because we've been talking about things in the heap, right? We're talking about Malloc, we're talking about free. They're all happening in the heap. They're all happening like getting memory space within the heap for us, returning memory space within the heap, and so on. But this aside, we need this operator, so I want to talk about it before we go back to the heap. There's this operator called sizeof, okay, in C. And it's very useful, where it's going to figure out how many bytes. So remember how Malloc asks for how many bytes we need for space, and then it looks for it, right? So what sizeof does is it tells us how many bytes we actually need for a particular data type. So let's say if we want to have enough space to store an int, we can say, hey, we can ask sizeof, hey, how many bytes does int actually take? And then get sizeof to figure that out before we get Malloc to get some memory for us, that amount of space for us. Does that make sense? So we're basically asking the computer, hey, how much memory does a particular thing take up? So sizeof int. I've got this code here. I did not write this code. Sasha did from a previous term. But I thought it was quite nice, so I wanted to show everyone when it loads. Okay, can we see properly? I hope we can see properly. Let me know if it's not. But what this program does, okay, is just, it prints out what sizeof returns to us, okay? So it's calling sizeof on a bunch of different data types, right? or different variables, depending on how you use it. Generally, I like to use it with data types, depending on what we're talking about, actually, because arrays are different. You just shove the array down. But anyways, so the first one, we're printing out the size of int. The second one, we're printing out what is the size of this array we've declared here. Like, how many bytes does it take? Yes? I was waiting for someone to ask that question. So that is an unsigned int. So it's int. You can think of it as like it's going to print out integer in this particular case. Oh, I'm not sure about that actually. If you Google that, let me know. Let me know, because I haven't looked into unsigned int too much. Do you know? Do you guys know? What as in like what it stands for? LU? Was that the question? What it stands for? Sorry, what was that? What is stored? It's an unsigned integer. Yeah. So, but do you guys know what LU stands for? Long unsigned int kind of thing? Not quite sure, but unsigned int is the buzzword that you can have a look up and have a look. But yeah, that is outside, like we won't be using this in the course. We're just using this here in this case because sizeof returns this particular type, unsigned int type. Okay? So, if I compile this, oh no, I want to sneeze. No, I can't sneeze. Okay, if I compile this, and run it, it's going to very nicely print out how many bytes each thing is, right? So an int is 4 bytes, and we didn't write 4 there. We just wrote, hey, size of int. Can you tell us how many bytes it is? An int is 4 bytes. That array that we have here has 10 integers in it. So it's 10 times 4 bytes. So it's 40 bytes, which is what it says here. A double is 8 bytes, so a double is double the size of an int. And then we've got a char, which is 1 byte, okay? It's much smaller than an int. You can have a play around with this. This code is accessible on the course website as well. So this is what we have. Okay, does anyone have any other questions about this? Yes?
I thought characters were just ints.
Characters are just...
We were presented as ints.
Okay,
How is it smaller?
that's a really good question. So characters can be stored inside an integer variable. So your A, B, C, D, E, F, G, or like your exclamation marks and so on. They can be stored inside an integer variable, but they can also be stored inside a char, which is much smaller. Because you can think of it as, because it can be stored inside a char, so that it can be stored inside a bigger number. And what characters are, right? If you remember back to the ASCII values, they're actually stored as ASCII values, so they're actually just numbers, right? I think the lowercase a is 65 or something, so you're actually just storing 65. So this is a sidetrack, but I want to show everyone this. I don't know, like, some of us might already know this, or maybe, I don't know how obvious this was, but let's say this is not part of the lecture content, just bear with me for a second. But let's say if I had no, I'll just do it with an int. Let's say if I'm making a int character A, right? I can print that out in 2 ways. It doesn't matter whether that type is an int or a char. I can print it out as a character, and I can print it out as an int. I wonder if that answers your question also. Can you see that? So if I have an int there, that just means, hey, that storage space is 4 bytes in this context, and it's storing the ASCII value of A, which is 97, not 65, sorry. Why did I think it was 65? 97. And so with that same thing, you can print it out as the character itself or as the integer kind of thing. So you can think of it as that 97 is getting stored inside a smaller space, which is 1 byte. And the value of 97, because it's not that big, so then it fits inside 1 byte of storage space. And when you are like storing in 4 bytes, it actually technically doesn't need that the other 3 bytes. Does that answer your question? Okay, cool. Any other questions? Yes? Percent D? You can give that a go. I think it's gonna, DC6 is gonna complain. Because the return type of, the size of gives something different. But we can try. I'll just change 2 lines. It should complain if it's not right. I have no clue. Let's have a look. Yeah, it's gonna give a warning. What happens if I force it to run, actually? Oh, it's still, okay. It still runs, but it gives no warning. Yeah. Yes.
Yeah, let's say we have a separate function. If we malloc something inside that function, can we use it outside the function?
Really good question. Yes, you can. And
So basically creates a global variable.
not quite. Remember how the memory diagram we had? Global variable at a different place. But in the sense of like you can use it everywhere in the program, sort of, but you can't directly reference it. You need to return it to use it. I'll demonstrate that. I think I have a code example to demonstrate that later. But if you return that piece, the address to that piece of memory, because the key is you need the address to be able to access that piece of memory. So if you return the address from that function to a different function, then you'll be able to access that piece of memory. Does that make sense? So it's not quite like your global variables where, you just refer to the name and it's just everywhere kind of thing. Yeah. Okay. Cool. All right, so keep in mind the sizeof. That's just a mini, well, it turned into a bigger aside, but yeah. So we've just talked about malloc, we talked about sizeof, we talked about free. Malloc and free are like kind of opposite. Now we're going to put it all together, okay? And this is generally how we would use malloc, okay? Since malloc takes in the number of bytes and sizeof gives us the number of bytes of a particular type, we can make use of that. And what this example is showing is, hey, let's say if I wanted some space to store 10 integers, so it's kind of like array of 10 integers kind of thing, okay? Let's say if I wanted to store 10 integers, hey, malloc, can you give me a space enough to store 10 integers and return the memory address to, so that my int pointer can reference it, kind of thing, can refer to it. Yes?
So normally if we wouldn't have used malloc, it would have created a stack. Because previously you said that it creates a stack element.
So the function, when you have functions, they create stacks, but malloc's in the heap. So even if you're calling malloc in a particular function, you're kind of allocating memory in the heap. Yeah, for that particular thing.
Is this the way to initialize it, you would say?
Yes, so that goes back to your original question about how do we initialize pointers, right? This is one way to initialize it, so then you get memory pointed to it. Yeah. The other way was what we showed before. Yeah. Any other question from that side or from this side? We're very quiet on the both ends. Okay. Yeah, so I know I put a 10 times size of int. You can technically just have size of int there if you just want one int, for example. So you can like do however many you want kind of thing. This is just an example. But this particular thing will give you 40 bytes, since size of int, we saw from the example before, was 4 bytes. Yes? Really good question. So the question was, I keep forgetting to repeat it for the online people. If you're allocating memory to the pointer, how does this initialize it? Now remember what a pointer variable is. The pointer variable is a variable that stores an address, right? Malloc is giving us a storage space and returning us the address of where that storage space is. Okay, so it's storing the address of that storage space. Even though that storage space itself might not be initialized. So the thing that the pointer is pointing to is not initialized. But the pointer is initialized because it's storing the address of that memory space. I hope that didn't confuse anyone. Okay, cool. No worries. Yeah, okay. Cool. Moving on. So yeah, this is the general kind of structure that you might want to use. X being an arbitrary number, any number that you want. Well, any number that you need in your program. And like we said before, we want to prevent memory leaks. So we need to have a free at the end. So if you're like saying, hey, int pointer equal to malloc something, then make sure you free at some point in your program. Okay. Perfect timing. It's 101. 101. What time is it? Oh, okay. Let's do a Kahoot. Give me a second. It's already 101. Do we start at 11? 12, right. Yeah, that's... Okay, never mind. We're good. Perfect timing. Kahoot time. Sorry, I'm lacking some sleep from last night, so my brain is not at its best condition. Let's do a Kahoot. We're good. We're on time. I thought I was like, how did I talk for 2 hours? And we can take a break in the meantime as well. And if you want the Kahoot, come grab chocolates. Online people, please, you can join as well. Let me do the settings. Yeah. Where's the music? For some reason, I thought we started at 11. I don't know why. That's so odd. If you need to go to the bathroom, take a break, feel free to do so. We'll probably do the Kahoot and have like 10-ish minute break so we get to 1:13 or so. Yeah. Write that down. Music is louder than my voice. Okay, I'll turn down the music. Can you guys still hear me properly online though? Like, was it clear the first half hour? Although I think a lot of us had only the left ear. I'm so sorry. Okay, cool. Thank you. We've got 56 people on there, 58. We're still joining, so I'll give it one more minute. Wait, I saw a name that said, I hate Pac-Man. Are you guys traumatized by assignment 1? I'm sorry. We thought to make it fun, so then we were like, Pac-Man seems fun, you know? And so one of our tutors... Oh, I'm so sorry. Okay, it's still growing. Number's still growing. Come on, everyone, join. How many people are online? I think the number is growing, dropping. I gotta start the game now. Sorry. There's a code at the bottom right. You can join. There's still a few seconds. If you have a variable int a, how would you get the address of it? Wait, where did the music go? Yes, 68 of us answered. Percent 8. The asterisk one, oh, that is the pointer notation. But remember, that one's get the value of where the pointer is pointing to, not the address of. The address of is always the ampersand, okay? Okay. Oh, is this yellow eats? I love yellow eats. Anyways. Next. How many stack frames do we have when the code is executing at line 6? So who was listening in the first hour when I was talking? I hope this is relatively nice. Yeah, there's only one stack frame because when we look at line 6, it's before the function call to foo. So we've only just jumped into the main function, right? So only the main function stack frame has been created. How many stack frames do we have when the code is executing at line 12? I'll fix it up.
Yeah, 4. You had it as wrong, but it's technically right because you're dereferencing and then assigning it a number.
Okay, I'll correct it. Okay, nice. It is 2 because we have 2 function calls on line 12. So by the time we get to foo, and then it jumps into foo, which creates another stack frame. So we have 2 stack frames, one for the main function, one for the foo function. How many stack frames do we have when the code is executing at line 22? Let's have a look. This one's debatable. Line 22 is here, right? So we went from foo, so main function, then foo, then bar, then we called baz, okay? So there's 4. Don't forget to count the main function. How many stack frames do we have when the code is executing at line 14? Line 14. Okay, so we had the main function at line 5. Then we jump into foo, which is line 7. Then from line 7, we jump into bar, which is line 13. And then we return from bar. So one of them gets destroyed, right? When we return from the function, the stack frame gets destroyed. So that's a trick question. It looks like 3, but it's actually 2 because we just returned from bar. Okay? We just returned from bar on line 14. What is the correct way to Malloc 5 integers? Okay, so yes, exactly. The green one is correct. What's the next most popular one? I mean, with integers, we want to use the size of function. Kind of here. Here, the best answer is the green one. Nice. We've got 2 more questions, so let's see who comes out in the top 3. Okay, so obviously it doesn't really do anything useful. I don't know how many of us selected that one? 3? Yeah, so here we've called Malloc, but we never called free, right? So there's actually some memory floating around as we're going through the program. It does get freed once the program ends, like all the memory associated with the program gets freed when the program ends, but we want to have free in the code itself. Last one. Oh, okay, last one. If free isn't called, does memory ever get released? I think I kind of said the answer as I was explaining the last one. Oops. Let's see who was listening. Okay. So let's see who are winners. Drum roll. Nice, congratulations. Congratulations. Nice. Are you guys all in the lecture or are we online? Can the top 3 please come if you're here and grab a chalky? Luke left me, Krish, an empty entity. Online, you're online? If you come to the Friday lecture, I'll give it to you. No worries. No worries. Yeah, I'm not sure which name associates with you, but barrel, yeah, if you come online, if you come in person on Friday, I can give it to you. Just come up to me. Okay, Krish, okay, yeah. Yeah, if you happen to come or on campus or at uni on Friday. Okay, before we continue, settle down a little bit. We're getting a little bit excited. Before we continue, I just want to go back to something before. Thank you so much, Gab, for putting it out because I don't know why my brain did not think right. Okay, this slide, I will correct it in the slide after this lecture, but there's a mistake in the slide and I said it wrong, so I want to clarify here so we don't confuse anyone after. Example 4 is actually valid, okay? I need to draw a diagram just so that I am showing you guys what's actually happening and not confusing you guys with a yes or no answer. So let me do that now. I didn't expect myself to draw too many diagrams today, so I'm just going to work with my laptop. Bear with me. So here's the thing. We have an int number. So I'm just drawing a box. Oh. I'm just drawing a box to represent where the number will be stored. So this is our int number. And then we have another storage space, which is the number pointer. Let's see what's happening in this example. Okay, so that's what's happening. And this number pointer, since it's a pointer, I'm just going to draw an arrow. It's currently uninitialized. So, I'll explain 4. What's happening at 4, Gab, correct me if I'm wrong, because I'm not trusting my 3 hours of sleep last night. But here's what I'm going to say. So, when you have, so let's say if they're both uninitialized, and you execute the line on the example 4, what's going to happen is you're saying, hey, can we go to the number pointer, follow where the pointer is pointing to, so go to the address of where it's pointing to, and update that thing to be whatever number is, whatever's in here. So let's say, hypothetically, let's say there was a 3 in here, then we're updating here to have the value of 3. However, note that both of these are uninitialized, meaning this number pointer is not pointing at anything right now. It's not pointing at any particular storage space right now. So if you try and store a number in the thing that the pointer is pointing to, here, it's going to cause an error. It's going to not work, okay? However, if before your example 4, that particular line, you added a line to say, hey, let's make number pointer point to the address of where number is. Let's say we do that first. Then we do not line 4, where we say, example 4, sorry. We say, hey, go to where number pointer is pointing to, and the storage space, and make the value there to be number. If we do something like this, so this is what example 4 is on my slide, right? If we add a line before that, then this will work. So in this particular case then, what's going to happen is we're saying, hey, can you first make number pointer point to where number is? Or can you first make number pointer store the address of number? Meaning, if I use my arrow notation to draw it, I'm making this pointer lead me to this number variable, okay? Like that. Let me rub this off. Like that. then if I now that the pointer is pointing somewhere or leading us to a memory address, an actual memory address that has a storage space, then we can say, hey, make this thing equal to number. Technically here you're saying, hey, make that variable equal to itself, kind of thing. It's valid in this case. So as long as you assign it to some variable first. Is that right? Yeah, okay. Yeah, the second line doesn't have to be number. I can make it, so let's say if I do, the second line said asterisk pointer is equal to 5, then what that's going to do is it's going to follow that pointer to the variable and store 5 in there. Hopefully that makes sense. Let me know if it's confusing. I really wanted to clarify that because that was a mistake, or it's very confusing on the slide, so I'll make that clearer later. Okay. So let's move on then. We're going to bring all this together and write a program. Okay, there we go. So we're going to write a program. And what we're going to do for this particular program is focus on dynamic arrays, because we now know how Malloc works, and we can now Malloc a piece of memory that's going to be able to store us a collection of numbers or collection of data, okay, an array of data. So we want to read in a size from the user saying, hey, how many numbers do you want to store, let's say. And then we're going to create an array of the size that the user has said, rather than creating an arbitrarily big array. And then we're going to scan in inputs for the array, and then we're going to reverse the array and print it out. Okay, we're going to print out the array in reverse, kind of thing. So that's the task we have in hand. Let's do that together. Okay. Because I'm not going to want to switch back and forth, I'm just going to copy and paste this into my reverse array file, which I already made, which you guys should be able to access. So every time I save, it should update if you refresh. And I'm just going to, it's not pasting. Never mind, I'll just do it manually, that's okay. Okay, so let's just add everything that we usually add into our program here. Okay, first thing we wanted to do is read in a size. Okay, so what I'm going to say is read in a size. So we can say, let's have an integer, because we want to read in a size, and ask the user, hey, how many numbers do you want to store? Like that. Okay? I'll put a colon. And we're going to scan in that number. Okay? Now we're going to use this value to create some storage space. An answer worth a chocolate, and someone who has no answer before yet, an answer worth a chocolate. What is the line that I will write probably with Malloc if I now want to have a big enough memory space to store however many numbers that the user wants me to store as integers? So what is the Malloc line that I want? Yes? Malloc size times size of int Is there something else we also want in there? Assign it to a pointer? Yes! Oh, I didn't give you a warning. I'm so sorry. I'm just going to... assign it to a pointer. Yes. So, because we want to be able to keep track of that piece of memory. Wait, I did say I was going to ask someone who hasn't answered. Anyways. So, like that, right? So I'm saying, hey, pointer, can you point to whatever Malloc is going to return as the address? Store what Malloc's going to return as the address, kind of thing. So Malloc, what's going to happen is, it's not like we're not in an ideal world. If you ask for memory, you should have it should give it to you and stuff. But there's a limit to how much memory there is in the computer, right? Depending on whether you have a 16 gig RAM or I don't know what you guys have, but mine's 16 gigs. So it might refuse. And how Malloc refuses is it returns null, okay? It returns this thing called null when it refuses, okay? You can understand null as in nothing. I've got nothing for you. It's basically the zero address in, like, number zero, address zero in memory. But it just means nothing. In this case, you can just think of it as arbitrary thing. That means, hey, I don't have anything. So if numbers is null, it's pointing at null, which means it's not pointing at any address. Malloc couldn't give us any space. Okay? So in this case, we might be like, uh-oh, sorry, no space. And just return. Okay. I'm putting return 1 here just to differentiate from the return 0, which in this case means, hey, we've successfully ended the program without any unnecessary issues, and just return 1 to differentiate that. Okay, so if that if statement is false, it means that we have gotten a piece of memory. So then we skip this if, and we will reach this line, okay? The stuff after the if. Do we have a question? Yes. We'll get there. We'll get there. Okay. So what we're going to do now is we're going to use this storage space, scan in values from the user, and store it in this particular space. Okay? What I'm going to do is I want to create a function to do that for me. Okay? I'm going to call that function read array, because we're going to read an array of integers, okay, into this storage space. We're dealing with dynamic arrays here. So in order to read in the numbers, I need to first know where I need to store the numbers, okay? And this numbers pointer, you know what? I'm going to change this to say numbers pointer because we've been using PTR as the ending for all the pointers, so we're not getting confused. Kind of thing, okay? So yeah, so in order to read into an array, we need to have the space to read into, which is what numbers pointers is pointing to, and we need to know how many numbers the user actually wants us to scan in, right? So that's what we want. So based on this is the function call I want, right? I'm going to create a function for it. So numbers pointer is a pointer type, size is an integer type, and well, we don't really need to return anything, so I'm going to put void. This is my function prototype. So I'm going to copy and paste that, put it at the top. We always need our function prototypes. And then we're going to write the function. Read array. So, like we do with our assignments in our labs, we just have a loop that's going to go through the size, okay? Size times, because size was the value that the user entered to say that's how many numbers they want. So we're going to loop through size times and scan in numbers from the user until we reach size. So while I is less than size, I plus plus, and I'm going to say enter a number, please. And I'll scan in just like we normally do. We're scanning integers because we want an integer. We want integers, sorry. And we're going to scan in. Okay, this is the key point here. Malloc is going to give us a contiguous block of storage space. And that storage space is pointed to by the number pointer. So I can do this. Did I spell numbers pointer with numbers and number? I'll fix that up later. Anyways, so I can do this and say, hey, go to the memory space that you're pointing to and access the 0th one, the first space, the 0 space. Okay? So your pointers, in this case, like when we were dealing with arrays, it's very much like we're dealing with pointers in this case, except when we were with arrays, we couldn't move the pointers around. I think Jake showed you guys how to like do pointer plus plus and so on in the last like 2 weeks ago, kind of thing. But yeah, so that will refer to the first thing, and because we're scan effing, we need the ampersand in front, right? So I'm just adding the ampersand because of the scanf. So that's going to scan into the 0th element, but because this is a loop and I want to scan into the next thing, into the next thing, into the next thing, and next storage space in the array, right? In the storage space, in the contiguous storage space. So I'm going to just put I there, right? Is anyone, let me know if anyone has any questions or want me to go over that again, because it can be confusing. Okay, so that's that. That's going to read it directly into our numbers pointer array, right? And I want to just check that. So I'm just going to do a print array function that's going to take in numbers pointer, which is pointing at the storage space that's storing all our numbers, and size, which is telling us how big that is. And we're just going to go, hey, let's loop through it. Let's loop through it and print out. Apologies, my laptop is not feeling very well because it feels very laggy every time I type. But let's go here. Like that, okay? Because we can refer to it like an array now.
Should it be numbers?
Yes, it should, indeed. Okay, so we've got a function here, so I need to do the function prototype at the top. Always don't forget that. And I want to call this function just to verify that I've read in my array correctly. So I'm going to say print array, pass in numbers pointer, and the size, okay? So it should just read in a series of integers from me, and then print out the series of integers that I've, entered, if I compile. And there's no errors. I'm just hoping for the best right now. Semicolon, oh, classic. Okay, line 4, my function prototype it must be, yep, save. What's happening here? What do I need to do? DCC is getting too smart. It's just telling us all the answers. Yes, standard lib. I was gonna asked everyone that, but DCC literally just wrote it out, like usual. Okay. We need standard lib here, remember, because Malloc comes from here, okay? And we're using Malloc here, line 13. Oh, didn't save. Saved. Compile again. Okay, let's have a look. How many numbers do I want to store? 5? Did someone say 5? I'll do 5. 1, 2, 3, 4, 5. There we go. I'm not very creative. Oh, no, actually, never mind. I'm not doing 13 numbers. Yeah, so basically, it worked, right? It's printing out what I entered. So, great. It's storing inside the Malloc piece of memory. Now let's do a reverse array, right? We just need a reverse printout, because that was the original task. So instead of print array, we just go, hey, since print array is going through the array in the right direction, we want to go in the opposite direction, but with the same loop, okay? So rather than starting from 0, I'm going to start from size minus 1, because arrays start from 0. And then I'm going to go up, go until less than or equal to, well, I is greater or equal to 0. I'm going to keep looping. And now print I. So instead of counting upwards with our print array, we're counting downwards. Yes. Yes. You've been paying attention. Now I need to do function prototype. Again. And I'm just going to, instead of print array, I'm going to just do reverse array. So in theory, if I do 1, 2, 3, 4, 5 again, it's printing out 5, 4, 3, 2, 1. Okay? So that's how we kind of, you know, allocate memory upon request of how much we want. We no longer need to do 1024 storage size arrays or 5000. I don't know what you guys are like. Yes?
I have a few questions. So, firstly, why do you call functions? Like, as in your terminal, it's only returning like 5, 4, 3, 2, 1, and you have two functions that are ascending and descending. So why does it only choose descending?
Oh, I did that really quickly. So, sorry, I should have explained that. I commented out the line that was ascending.
Oh, wait, but isn't read array?
Read array is the one that's scanning in the numbers. So when I was typing in 1, 2, 3, 4, 5, read array is scanning in.
I didn't notice it.
It's confusing because they're very similar. Yeah.
And then, why don't you have a free?
Because I was deliberately leaving it out and I want to demonstrate the error that I would get. Very good. You guys both spotted it. I'm sure a lot of us also spotted it. Now, if I don't have a free, right, that's a really good question. We're going to have a memory leak. And how, when you're doing assignment 2, you will need this tool. -- leak check, okay? I haven't used it in a while, but if I compile with -- leak check flag at the end, this is very important. It's not going to do anything here, but when you run the program, at the very end, it's going to tell you something. It's going to say, error, free not called for memory allocated with malloc in function something something. I don't know why the error is really weird. But point is, we haven't freed our malloc memory in our code, right? So it's complaining about that. So the reason why I'm showing you that is when it comes to assignment 2, spoilers, you may have places where you need to look for memory leaks and make sure you don't have any memory leaks. And so dash leak check is your best friend in that. Yeah, to check whether you have any leaks, okay? So in order to fix this, we just go free at the end, like we've said. So if I compile it again and run it, how many numbers do I want to store? Let's do a different number because I keep doing the same numbers. 6, 3, 5, 2, 9, 10, 11. Hmm? Ah, what's happening? What is happening? This is a classic bug. I had to think about that one for a second. It's still telling me, oh my gosh, I didn't deliberately do this, but this is such a good example to show. Because this is such a common bug in people's assignments when you get to assignment 2. It's still giving me that error. It's saying I have a memory leak, but I have a free here. What's happening? Let me show you the whole code. What is happening? I saved. I swear I saved. There's no dot, so when you don't save, there's a dot at the top. I did save. Leak check is working fine, I think. There's something there. Something's missing. You get 2 chocolates if you figure it out. I'll just put it here, just to tempt you guys. Maybe you can figure out the answer. I have a hint. Look at where we're mallocing. And like the location, the line we're mallocing in relative to the rest of the code. Yes.
Shouldn't the free numbers next to be next to the malloc?
Well, are you talking about like putting free after the malloc, or like here? Because if you free there, right, you're gonna use it later. Like if you free, is this what you mean? Like putting free there? Yeah, because the issue if you free there, when you use it here, like in read array, it's going to cause issues, right? Because you still need that piece of memory there to read in the array and so on. Oh, this is such a good bug. Yes. Does it need to be after I've called the function? It is indeed after I've called the functions. I'll run it again just to make sure that I'm not lying to you. It is indeed after. I'll use the normal set of numbers. 1, 2, 3, 4, 5. Yes?
Numbers PTI is being used 2 times, so I think inside the function we have to use it separately so that it clears the what's that called? Memory, and then we can reassign it to something else.
Good try. But all we care, so when we're talking about free, all we care about is the malloc. So if it's malloc once, we just need a free once kind of thing.
Do we have to malloc like the number of times it's
We've malloced it all together as the one thing. Notice how this is like size? So it's malloc the whole array together. So we'll free the whole array together. Yes?
You should put free inside the if numbers pointers equal to null. Because if it's null, it will never be reached.
I think the chocolate bar is going to you. Let me just double check. Let's do that. So the answer was we need to put this in here as well. Okay? Let's just double check that that works before I start explaining and think that that works. I believe that works, but I don't trust my 3 hours of sleep right now. Wait, give me a second. 2 seconds. Yes?
Can you move the camera to like the other side of the screen? It's blocking the bottom.
Oh, I'm so sorry. Give me a second. And that gives me time to try to figure out what my brain is thinking. Let's put it there. I think that should be fine. One sec. Let me just think. Never mind. That is not the error. That is not what I had in mind. But that was what I wanted to show, but I think this is the wrong example to show. My bad. I'm sorry. Ignore what I said. But I don't know what the memory leak is. Does anyone know? Do you guys know? I have to loop through them. Let's try that. One sec. Sorry, guys. I messed up a little bit, but that's okay. So, we're saying we want to loop through. I thought you can free it together, but no. Like that? Let's try that first. Just bear with me for a second. Oh, I'm getting more errors. What am I doing? Size, because it's less than size, we don't want to use I anymore. We want to, what's that? Pointer? Yeah, but if we're using the number pointer, we're no longer incrementing. We're plus I plus 4. Size. Let me come back to this one. I'll get back to you guys, I promise. My brain's not quite working right now. If anyone is confident to come up, is anyone confident to help me solve this? Because my brain is not working. Yes. My brain is not working. Otherwise, I'll get back to you guys about this one in the next lecture. Oh, the error message, okay. Well, this is wrong here. If I go, because I can't do the square brackets because it's asking you need to free the address kind of thing, free passing the address. Like this loop is wrong. But I'll scroll to the error message. Yes. Try freeing. I see what you mean. So, but the thing is, I can't use. Do you want to come and help me out? Thank you. I'm a bit stuck, so we're getting a bit of a rescue here. I'm sorry, guys. One sec. Gab is coming to the rescue. Yeah, I'm like.
Because if you free number's 0, then like
I thought it
there's no
was
reference to it anymore. Is that the name of the array?
numbers pointers.
Well, what is its size?
I thought you can do the whole thing together. No?
It's only for static ones.
Okay.
For dynamic ones, it's like it's a bit different. I feel like maybe that.
No.
Oh, chuck int in front of it.
No.
Is it an error or a warning?
Because where free wants a address. Oh. Oh. Okay, we'll leave that as a homework for you guys if you have an answer. Otherwise, I promise I will get back with an answer on Friday. But let's leave it with a memory leak for now. Yes? Sorry, I can't hear. Give me one sec. Oh, wait, one sec. Is that what were you saying? I minus minus? Oh, yes, indeed. Let's see if that works. Oopsies. Let's see. No. Homework, guys, homework. But the bug I thought it was, which it wasn't, but I still want to mention something about it. It's not this, it's a different thing, but I kind of want to describe the common bug that you encounter in Saboteur. So I'll leave this as homework, and I promise I'll get back to you with an answer on Friday before we start the new topic. But the common bug that you have is often if you have a structure where you malloc something, guys, and if you have an if statement, okay, in this case because it's checking whether it's null, so it's different, but if you check for something else, let's say if you had some condition like, if you had some number and it was like less than 5, like if you had some condition there and then you had to early return, you have to make sure you free in here. So, yeah, what we were talking about before was the answer I was looking for, but it was in the wrong context here. So just ignore that, and I will figure out what's the issue here with the memory leak, because I can't seem to figure it out, and we can't seem to figure it out, and none of us seem to figure it out. I wonder if there's like an issue with. I'll have a look. I'll have a look later. But yeah, that's that. But there's one more thing I want to show. So let's just assume that there's a leak. Let's just leave it with a leak, which we don't like. But we can resolve, or if you guys have answers on Friday, I will get you to come and code it up. So let me just check this is back to before. Okay, it's back to before the memory leak, okay? Now, what I want to show, the other thing I want to show is having this malloc within a function, inside a function, okay? Because I want to show that it can be carried across to the main function. So it's just a demo. There's not really a meaning here to put this in a function. But I'm going to put this in a function. I'm going to call it create numbers. All right. Okay? So what I'm going to say is, hey, if you give me a size to the create numbers array function, I'm going to malloc, okay? Instead of mallocing here, instead of mallocing here, I'm going to malloc within the function. Okay, I'm going to malloc within the function. And return it. And then I can use it here. So there's not really a purpose because you're writing an extra function for one line of code. But I just want to show the fact that if you malloc within the function, like once the function returns, you still have that piece of memory kind of thing. So what I just did was I moved the malloc into create numbers array. And in create numbers array, I'm mallocing and then returning the memory that's being malloced. Let me just put the function prototype at the top first. Okay. And then I am doing the rest of the code as it is. Line 33, I've spelled something wrong. Yeah. So you see how it's still working as it intended? But the difference now is our malloc is now inside a function, okay? So once the function returns, everything else related to the function gets destroyed, but that piece of memory, because we return the address of it, it gets stored inside this numbers pointers variable, okay? And then you can continue using that piece of memory. It carries across the entire program. That's the thing I wanted to show. Okay. So there's a realloc thing, but that's extra content. It's not actually accessible content, but I've left it in the slides. So if you're interested in knowing how do I grow the space, like once your array fills up with malloc, right? Let's say if you wanted more, if you want to add onto your space, like patch more space onto it, how do you do that? You use something called realloc, okay? That will extend the space you have, kind of thing. Now, there's a little bit of a like a accident or incident in the middle, but I'll give you guys an answer about the freeing, what happened to the memory leak on Friday, I promise. I'll come back and that's the first thing I'll say. But I would really appreciate if everyone could give me some feedback, everyone online and in person to help me improve. And thank you everyone for coming and listening. And yeah, I'll see you guys on Friday.
You can do you can assign the number pointer, and after free, assign to num, like in my work.
Are you talking about the code?
Yeah.
Thank you very much. Thank you. See you.